Here we go. Let's give it a shot, see what happens. We will look at the derivative. Not only as a symbol, but as a quotient. Now that one doesn't look like a quotient, does it? No. We also know in your textbook there were 4 or 5 different ways of writing the derivative. One of them is dy over dx. Okay? I kind of brought this up earlier, that the derivative is the slope of a line that the instant it's at a point. Instantaneous velocity, right? How many points do you have to find the value of the derivative? 1. It's closely related to the actual slope of a line. F of x1, f of x2, all over x2 minus x1. This is just the slope of a line containing 2 points, known as the average velocity, correct? There was another symbol for this called delta x over delta y. Oh, sorry, I got that backwards. It's delta y over delta x. The y values are the function values. Function values are y values. If you want to go all the way back to algebra, without function notation, you can write that as y2 minus y1 over x2 minus x1. You want to do that, you can. But that third thing I wrote right here is the key to part of this lecture. This is the actual difference between x, and this is the actual difference between y. That means the actual. Okay? This is known as the approximate. But the approximation is so good that we call it good. Okay? The approximate is so close to the actual answer that we say, you know what, this is better than the actual answer. We're going to use it for our solutions to answer these questions on our problems. So, the differential blank is an independent variable. Well, I think they're talking, anytime they talk about independent, they're talking about the horizontal axis, the independent axis. This is the dependent axis. Independent can mean time. It can mean, what do we talk about here sometimes? Oh, it can mean the real, if you're talking about complex numbers. But usually we call that x, don't we? And usually we call the vertical y. Where's your pencil? Get on that paper. The differential dx. The reason I put differential there, I put the x because it said independent. I put differential because it said, or I put the d because it said differential. So dx means the differential of x. That is the approximate change in x. Yes, differential has derivatives in it. Okay? Now the actual change in x is delta x. You notice the difference in the terms are close. dx stands for the differential of x. Delta x stands for the actual change in x. Very closely related. You're right, but one of them's using 2 points, the other one's using 1 point.
Is that supposed to be x2 minus x1?
Yeah. So one's using 2 points, one using 1 point. One is an approximation, and the other one is an exact value. Okay? So if you want to find the exact value of the square root of 51, you write the square root of 51. If you want a decimal approximation for the square root of 51, you punch in your calculator, you get all the decimals. Okay? There we go. That's close. Okay? Thought you might not be coming back for a while. All right, here we go. Therefore, the differential, what did we say the derivative equaled in the first blank? dy over dx. So we said that f prime of x equaled dy over dx. And we called this a quotient, didn't we? We called this a quotient. So that means if I multiply both sides by dx, I will have dy equaling f prime of x in the differential of x. That's huge in your school of thought. Because we said that delta y was equal to the difference between two y values, didn't we? Okay. The actual change in y, the actual change, I don't like it when you drift down and come back around and come back to me. The actual change is the difference between two y values. The approximate change is the value of the derivative times the differential of x. What do you mean differential of x? You've had the differential of x. Do you remember what delta equaled? This delta symbol, what did it equal? How close the values get to x. Wait a minute. That's delta. This is delta. And this is dy dx. It's all delta differentials. Yeah, they're staying within the same family of notation because they're all talking about the same thing. How far apart something is versus how close it gets at a certain point in time. In other words, how accurate are these approximate changes to the actual? Because the rest of your book, and look how thick it is. Pretty thick, isn't it? The rest of the book is based on the premise that these approximations are so close to the actual values that we can use these in our calculations. One, because they're faster, and two, you only need 1 point to calculate them. You don't need two, which can get very difficult to find. So you have to constantly keep aware of what's the approximate change and what's the actual change. Okay? Look at increments. I don't know what that means before using the approximate. Let's look at something like this now. Okay? I think we're ready to try this example. Let's say f of x, I could be wrong and lose half the people right now, equals the square root of x. Okay? That's an oldie but a goodie. F of x equals the square root of x. And let's say I have 2 points. Okay? Let's say I have 1 point, 1, 1. I put 1 in the equation, I get 1 out, right? And the other point is 2, 4, 2. Okay? So far, so good? Woo, woo. All right. This is my, let's get fancy.
No.
You want to get fancy?
No.
Oh, you guys are, okay. This is my starting point. Why do you need a starting point? Well, if you're going to change something, you have to have a reference point for the beginning of it before you change it, right? In other words, what did it look like before you changed it? It looked like 1, 1. Yeah. Yeah, you do. But the starting point is crucial. Okay? We'll talk more about that later. So I'm starting at 1, 1, and I'm going to 4, 2. Okay? The difference between the x values is equal to 2 minus 1, which equals 1, right? That's the difference in x. Oh, yeah, 4, sorry. I was looking at the y values. Thanks. 4 minus 1, so the difference in x is 3. Okay? Now, what's the change in y? Yeah, 2 minus 1, so delta y equals 1. Okay? Again, I use the 2 points for that, okay? That's in the actual way of doing it. Now, if I go to the flip side, I don't know why I'm in Halloween colors already. Let's say f of x is equal to the square root of x. X equals 1 and dx equals 1. The questions change. I have 1 point, I have 1 change in the point. what would dy equal? Well, dy equals 1/2 x to negative 1/2 times 1. Right? Yeah, the derivative times the change in x. Okay? So that means dy equals 1/2 times 1 to negative 1/2 times 1.
Why don't we multiply by the change x?
Oh, because it said the approximate change in y is equal to the derivative times the change in x. And that comes from the fact that the derivative can also be written as a quotient. Oh, you're right, it is. Whew. I was worried there for a minute. The change in x is actually 3, from 1 to 4. Oh, hush. I'm making this up on the fly to try to help. So, that means the approximate change in y is going to be 3/2. The answers aren't the same, are they? Delta y is at 3/2. The differential y, I'm sorry, is at 3/2, and the delta y over here is 1, isn't it? It's not the same, is it? But it's close. Sure, it's close. It's within 95%, which is within 2 standard deviations of your answer. Just kidding. Anyway, sure, it's close. You ready? 1, 4. This point right up here we said was 1, 1, didn't we? This point we said was 4, 2, didn't we? Okay. Are you ready? Here's the picture that goes along with the blue and the green ink. Everything has to have a picture, I hope. So, the actual change in y you found was y2 minus y1. You just took the y values and subtracted them, correct? And the actual change in x was the same as the differential in x. You subtracted them. In one you subtracted, 4 minus 1 got 3. And the other one, you're given the change in x. Okay? Yep. Yeah, dx and delta x. They both measure the change in x. Sometimes the approximate will equal the actual change. Yep.
Will d of x always equal delta x?
In your section of this book, yes, I think. I'm pretty sure, about 95% sure, that dx and delta x will be about the same. Because you have to start with an independent variable, and they're going to be the same. So, where does that derivative come from? The derivative calculates what? The slope of to the graph at a point, right? And we were a little high, weren't we? We were just a little high. This is what dy measured. Notice, dy did not give you a function value. It gave you the change in y. Not function value, but change in y. It only gave you the part from beginning to the end. It did not measure the distance off the y-axis. It didn't do that. Delta y doesn't give you the y value. It gives you the change in the y value. It doesn't tell you how far up you're off the y-axis. It just tells you how far you changed on the y-axis. dx doesn't give you an x value. It gives you the change in the x value. Calculus is all about measuring the change of something from A to B or at A. Yeah.
So is that like saying halfway point is 4, comma 2.5?
Right. This point right here is 4, comma. If I add 1.5 to 1, I get 2.5. Correct. 2.5. Okay? So that's what's happening. You're not calculating y values, and you're not calculating x values. You're calculating how points are changing on a graph using the derivative to do so. Your calculators are programmed to do this quickly. When you hit the square root button, do you think that there's a chart in your calculator programmed in? No. It's using an offshoot of this theory to give you the answers quickly to as many decimal places as you want. And when this gets going really good, your approximations become down to like the 8th, 9th, 12th, 14th decimal place of accuracy. Because you're just approximating the change. You take that change, add to the original, you got your answer. That's why you type in your answer to start. It takes that and adds to it this and gives you your final answer. We'll get to that in a minute. But that's basically what we're going to do. Okay? How's it going with the symbols? How's it going with what each symbol represents? There's a couple more things we have to add, but not until a little bit later. Okay? So, first time I've ever put an example in right here, but I think it was okay. I think we're ready to move on. All right. I know you're all anxious to do something, so let's get started. Let's do something. Oh, I'm going to hit the button. I have no idea what's next. Nice! Ooh! The yellow. I know. All right, Kaylee. What is the actual change in x? What's our notation? Delta x. Very good. So, what does x2 equal? Solve this for x2. Delta x plus x1. No, there's no values on this slide yet. Hence, I love the word hence. I must have been in a good mood that day. Hence, the initial value, x sub 0, changes horizontally by an increment of this means your initial value. The initial value, how far are you changing it? No. Changing it. Delta x. You have worked with this symbol. In fact, if you were in 7th hour trig, you've seen this symbol before. Limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That's how much it's changing. A little bit. It's not a coincidence. Your calculators are set up for delta x. How much do you want to change it by? Okay? Fantastic. I'll take this off just in case. I don't want to confuse Katie if I put these notes up online. Regarding the actual change in x, what's the symbol here? Delta y. So in function notation, f of x2 minus f of x1. Oh! Whoa. The difference in the y values would equal delta y. Delta y in function notation would be f of x plus delta x minus f of x. Sam, I need a ruling on this. You got your book open? No, you're supposed to be knowing what goes in the blanks to answer the questions in homework. Okay? This is just meant to lead me through so I make sure I hit enough topics so you can do some of the homework.
About what page are we on?
Well, I don't know, the next section, 3.5. So, what? f of x plus delta x minus f of x. That equals the difference between x2 and x1 in function notation. They mean the same thing.
Oh,
Okay?
It doesn't actually have.
Okay? Am I close? Woo! All right. Hence. Oh, there's the word hence again. Hence, the vertical changes in y can be expressed as blank, aka the increment of y. Yeah, delta y I'm thinking. And we called this a lot of different things. We called this f of x 2 minus f of x 1. We called this y2 minus y1. We called it a lot of different things. Okay? Wait a minute. That's a bit of a stretch. I don't think I'll go that far just yet. I was going to talk about the point slope formula, but I'll wait. The point slope formula. Isn't that y minus y1 equals m times x? x1?
what?
It's all related. The point slope formula,
Oh yeah.
Is that important to this right now?
it will be because, woo, all right, ready to move on? That slide went pretty good, I'm thinking.
What is
Yeah.
the point?
I don't think so. Later, I'm not too there yet. All right. No, this is the intermediate step we need before we get to the final answer. What is the slope of PQ? That's a question. Oh, wait a minute. Back, we're doing so well. Back up here. Oh, the slope of PQ is delta y over delta x, or f of x1 minus f of x0 all over x1 minus x0. That's the slope of a line between the 2 points. Look familiar? The equation of this line. We said the equation of this line is also y minus f of x sub 0 equals m times x minus x sub 0. That's the equation of the line. It contains this point. Okay? That's the point slope formula we used last week. So, what is the slope of the line tangent at P? How do you find the slope of a tangent line? Close? That is the normal line. The derivative, so it would be f prime of x sub naught. This came about, one, look at the ease of calculations for finding this versus finding this.
Outside of the line that you come across.
The derivative is tangent. You can cross a function, you just don't cross at the point.
What is that?
Point slope formula. Okay? How you doing, Grizz?
Not good.
Do you know what tangent means?
Just to go on.
Okay.
I want Lewis's head's in the way.
I know. No, that's correct.
Perfect. Quiet, please. Yeah.
You used to.
No, you're fine.
Yep. I use it because that was my starting point. 0 means initial. So my initial point was that point. And all this is just to give you a firmer handle on the language and notation that you're going to be using the rest of this chapter, next chapter. Okay? Oh, sure, you can sit there and you can, well, you better get a grip on this. This is going to be the bulk of your next quiz. Yeah. Yeah, the slope of the tangent line is the derivative. Because the slope of any tangent line is the derivative when you put in a number. Okay? The slope of a tangent line. Tangent line means instantaneous rate of change. When it's set at P, That means you put in the x value. Okay? Now, that's the derivative. That's the tangent line at P.
We have to write that stuff down.
No, I just want you to know where it comes from, because when you get to the final step, there's a lot of stuff there. And you got to know where it comes from in case you forget it. It all makes mathematical sense. It really does. Are you ready? And then you understand how the calculator works. And the more you understand how things work, the easier it is to figure out other things. Ready? I have no idea what's going to happen next, but I'm going to hit the button. All right. Find the general formulas for delta y and dy. It is. Oh, I'm not even halfway through. Ready? Find the general formulas for delta y. Ready? This is a general formula right here. Now, 4 people missed me. Pull this away from the right side of the board. This is what we're shooting for. Okay? This way, everybody has the same answer when they ask, what did you get? You've been doing this, only you've been using x plus a and a, or x plus h and h. Because it's going to change to a line, the equation of a line. And all your equations of lines have y's, m's, and x's. So your definitions need to change to y's, m's, and x's.
What do we need? What's this?
Well, dx means, well, I don't know, change in x, approximate change in x. You do. Also, in this example, dx will probably mean delta x. Okay? Now, I'm only going to use the delta x for the actual answer, and I'll use dx for the approximate answer. Okay? You want to see something really cool?
Yeah.
Look inside the front cover of your book for the second semester. Do you see all the dy's and dx's on the right side of the column? The dy's and the dx's? Oh, DUs, sorry. DUs. That stands for either one. That's where this is going, but it'll go there later.
That was not very.
It was. So, dy equals 3x sub 0 plus x squared minus 5 minus 3x sub 0 squared minus 5. Okay?
So this is the same thing as what.
This is a variable way of finding the change in y for any 2 y values. Okay? So, delta y equals 3x sub 0 squared plus 6x sub 0x plus 3x squared minus 5 minus 3x sub 0 squared plus 5. Yep, one's the initial point, one's not. Nope. Huh? No, there's no denominator. You're just trying to answer the question with what is delta y. That's the answer.
Well, that's just what we've done before.
Actually, no, it's not. Because if you chose x to be 0, what would be the y value that went with that? -5. If you chose x to be 1, what would be the value of y? -2. So here, if your initial x is 0, if x equals 0, and my change in x is going to be 1, I put in 0 for x, I put in 1 for delta x, and what do I get out? 0? That's not right. It should come out to be,
Yeah, it's 0.
comes out to be 0. That's not right. Something ran awry there. -3, 6, 0, 3, 1, 1, -2, 0, -5. Interesting. Huh. Maybe I got it backwards.
That's it.
Ooh. Sorry.
It's 0.
No, x sub 0 is my initial point. That's 0.
So then it'd be plus
You plugged in 0 for x.
Yeah. X sub 0 equals 0. X equals 1.
okay.
Yeah, so it equals 3.
That makes sense.
So the change in y is 3. I forgot the initial point was 0. Okay? Now, take a look at dy. You know what the definition of dy is, don't you? Yeah. So what's the derivative of that? 6x dx. Now, you're going to ask, aren't these, or why the different notation for dx? For one, you have to use this if you're talking about differentials. Remember, the derivative equals dy over dx. 2. Huh?
So that's
So
all it is.
how'd you get 6
Yeah.
from the derivative? How did you get 6x?
I use the power rule.
Oh, it's 6x subset 3x.
Well, I'm not worried about this. I'm just finding this.
Oh, okay.
Yeah, you leave the x in your answer.
That makes sense.
Yeah.
It was like 5. It'd be minus 6x minus 5 times 3x. Like, is it just the first part or is it the whole thing?
Whole thing. Right. Yeah. 6x dx. No. Huh. You're done. Thanks. All right.
Yeah, 5 minutes.
5 minutes? Yeah, it is. Find the values of delta y and dy if x changes from 2 to 2.1, y equals 3x squared minus 5. Okay. So, what is, do you have your calculator? Delta y means the function value of 2.1 minus the function value of 2. I don't know. What do you get? And dy, we had 6x delta x. Negative what? Negative 8.77. And what's 12 times 0.1? I don't think that's right.
Yeah, that's not right, because you have to put in 2 into the first one.
Yeah.
It's 2, isn't it 2.1 plus 2 on the first one?
Mm-hmm.
Oh.
You have to put those in.
Yeah. That's okay. 1.23. And this one is 1.2. Also, take a look at something. You put 2.1 in for the x, and you put the 2 in for the x, and you subtract them. The actual y values. Here, you don't compute any y values. There's no computation of y values. Here, this is only y values. You just subtract the two of them. Yep.
What's the formula for the
I used y2 minus y1, or f of x2 minus f of x1.
What is the 2.1?
The 2 came from my initial value, And the 0.1 came from my change in x. 2 to 2.1. Okay? Look, they're pretty close. Notice in the example how far they're moving. They're not moving very far, are they? A tenth. That's pretty far. Remember your deltas we did in your epsilon proofs? Delta was like sometimes a thousandth, wasn't it? So it's all really close. That's what we had to work with. So for tomorrow, I'm not sure how far we got. Is this one of the problems in your homework? So try numbers 1, 3, and 5. Give 5 a shot on your own. I'm sure you can do it.